All right, so we have, I guess we can start with the basic set of announcements. So everything is due Friday. The assignment and course project, and again, if you'd like to do a couple of both course projects, then I can give you up to half the credit as extra credit. That ends up being about 10% of the overall class grade, which is pretty significant. So I would highly think about at least giving a stab to both. Last time we were covering LL1 parsing, and we ended that with this idea of, well, if there are multiple elements in any cell in the LL1 table, then we know that that grammar is not LL1, which means we need more than one look-ahead character to derive what the appropriate production to use here is. Because there are multiple options and there's ambiguity, one character out. So we're going to take a look at another grammar. So how do we identify a grammar as not LL1? We look for a conflict in the table, and we're going to now look at such an example. So here we have as simple a grammar as I could come up with for an example. S arrow A capital SB or AB. So go ahead and start by calculating first and follow of S. And we're going to try to build an LL1 parse table for this. So first of S, how do we do it? We look at both productions. Both productions start with a terminal, which means there's no fancy work to do here. First of S is just A, regardless of which production you use. The first symbol has to be an A. So first of S is just A. What about follow of S? What could come after the non-terminal S? That first step is always to add dollar to this set, because we know that by definition, if it's the start non-terminal, then what follows that could be the end of the string. Yeah, dollar and B. Because if we use the first production here, S arrow A capital SB, then what follows that internal S could be a B. So we're going to union that into the set. And that gives us our follow. So the next step is to actually build the LL1 table. So let's do that next. What does the LL1 table look like? First of all, how many rows and columns does it have? It'll be a 1 by 3. We need that column for the dollar sign. That's probably what's missing. So we have an S on the stack. What could all of the elements, as we expand that S, what could we be looking for? Well, the only thing we could possibly be looking for is an A, right? Because that's the only thing that can start a string, given that we are trying to expand the non-terminal S. If we're trying to get a B or end a string and we see an S, there's no way to do that. There's no way to expansion that to end up resolving that into either a B coming first or nothing. But if we're trying to expand it and start with an A, then we have two options, which doesn't help us at all. We look ahead one character, we see an A, we still don't know which production to apply. So this means we can't decide between these productions. We look ahead, we see a single A in the query string. That doesn't tell us enough information to distinguish between which production to apply. So now we can think of building an LL2 parse table. To do this, we need to consider every pair of look-ahead characters. So how many pairs of look-ahead characters are there? So how is this going to change? How is this table going to change to make this an LL2 parse table? We're going to be mapping S to now pairs of characters. So there's still only one row, but there are going to be quite a few more columns. So let's go ahead and draw this table.
So we're gonna be K, A, A, B.
Yeah. So we're going to go from S to AA, AB, BA, BB, and dollar. Is that enough? Do we need to consider a dollar? Do we need to consider B dollar? Yes, we do. And we could still possibly end the string, right? Is that possible? If we look ahead of two characters? Luckily, these are all going to be blank, except for a couple of them, right? We only have these two productions. And if we go down these two productions, well, we know that AB, if we have a look ahead of two characters, we can get AB from the production AB. If we get ASB, what possible two character sequences can come from ASB? Just AA. And the reason is we have to read this A before we go into this production. Once we go into this production, regardless of which one we choose, it's an A. So one A, two A's, regardless of which one you go down. So we see two characters ahead. AA tells us to apply this production. AB tells us to apply this production. We get any of these other productions, we can't do anything with it. Or any of these other look aheads. BA, no way to produce it. BB, no way to produce it. A ending would still give us this. Well, that's not technically true. That's just A with who knows what after, but there's no way to actually end it with just an A. There's no way to end it with just a B, and there's no way to straight up just end it. So with an LL2 parse table, what do we notice? Do we still have ambiguity? Are there any cells with multiple productions in them? Multiple right-hand sides? There are not. So with a look ahead of two characters, it turns out that we can determine which of these to apply. So this is an LL2 grammar, not an LL1 grammar, because in the LL1 parse table, there's ambiguity, but in the LL2 parse table, there is not. Questions on that? How we feeling about LL1 versus LL2? Thumbs maybe? Does that help? So LL2, very expensive. Yeah, we ended up with that. All right, we're gonna go through another one. Following grammar is LLK for what value of K? Here is your grammar. And your task is to try to come up with an argument for this grammar. It is LLK for K of what value? And to make this a little bit easier, I'll give you this hint. Think about each non-terminal. And think about the level of look ahead that you need to be able to discern between the two options. So you have an S. How many characters do you need in order to know whether to apply A capital B or AA capital C? Same thing for B, same thing for C. Some of those questions are going to be easier than others. Some of those questions are going to rely on themselves a little bit. So try to find the easier one. You don't have to start by building the LL1 table necessarily. I would not do that. This is not LL1. We'll erase it. First of all, which of these non-terminals is easiest to start with? What did we determine?
As some of the uses.
I would argue S is going to be a little bit challenging because you look one character ahead and you can't discern, right? They both start with A's. All right, the second one starts with AA. Is it possible for the first half to start with AA? And it's like, yes, if that B becomes the first production in B, if this B becomes that, then we can have AA. So we can't use two characters to distinguish between these either. So we need more than two characters. But if we start with something like B, we can immediately, with a single character, figure out whether if you see A, apply this. If you see B, apply this. For C, if you see A, but if you see $1, then you're here. If you see AB, then you're here. So with two characters, you can look ahead here. With S, though, where does it stop? Can you figure it out with 3 characters? Do you need 4 characters? Is there no such constant? So the difficult one is S. How far of a look ahead do we need? 4. Need 4 characters?
Is A, so we come into A, L, A, B, C. So it's when the first is, it could still be, like the fourth one will tell you actually nothing. So it has to be 5. Or at least 5 to ensure that it's not B, that it's C.
Okay.
Because you can have rules and 2 B's in both of them.
Yeah, the equivalent question here is what is the longest string that you could produce? Where it would take us the longest to determine whether we wanted to apply the left or right. So on the right-hand side, kind of expanding this out, you have A, B versus dollar. So on the right-hand side, I think we can figure it out with 4 characters because it's that 4th character that makes a big difference. So we basically either see A, B, or we see A, and the end of the string, that dollar. So it's that 4th character that tells us, depending on which side we go down, but there's only really one branch.
We could change the C to C, I mean, or C to A to C, they're just, it's still A, B, and A.
Mm-hmm.
So does that matter now?
Yes, so that's just kind of what, this is just the right-hand side. We need to distinguish it from the left-hand side. So can we produce either one of these by going down the left-hand side? So, all right, we have A, and this B is going to be AB, which is going to be AB, which then we get to BC. Or we can get A, we can make a bunch more A's. We get down to this concept of A. And if we apply this rule again, we get another A before we have something we need to figure out here. Since this path can't be produced on this side, you don't have to worry about it. But the basic similarities are between the AAAB and the AAAB. But finish, this was a C, so this could be an A out here. But there's no way, this is the distinguishing character between the C and this A, about whether you're on the left-hand side or the right-hand side. So we actually need this 5th character to find the difference. Does that make sense? So this was the right-hand side. This was the left-hand side. So this mapped to that side, this mapped to that side. So to be able to determine the difference, we need a look ahead of 5 characters. Because if the look ahead is just AAAB, we can derive that from this set of rules or from this set of rules. We could go S arrow A capital B arrow. This B is now going to become AB. So we have AAB arrow AAAB arrow. Now we can do AAABC. And on the from the right-hand side, we're going to start with S arrow AAC. That C is going to become AB capital C. And then it doesn't matter where we go from here because we have to produce yet another A. But you can see that we produced this same starting 4-character sequence via applying productions from the left-hand side and from the right-hand side. So to be able to distinguish which of those we need to use, we actually need 5 look-ahead characters. How do we feel about that? Does that make sense?
So on the longest character you can get is left and right, the longest string on the right-hand side, that are both the exact same until it can't be the same.
Yeah, distinguishing between any number of these productions. So there's only a left-hand side and a right-hand side if there are 2 productions, but there could be an arbitrary number of these. The question is just between any 2 of them, what is the longest such string? I guess it's the shortest such string that you would need to figure out the difference between them, applying them. Because that removes that ambiguity. Because we want to be parsing this in linear time. We can't be doing a search. So if we look ahead 5 characters, we don't have to search. But if we look ahead 4 characters, we would have to search. Does it make sense why that is? It looks like there might be some questions.
Is there another example?
There is another example, but not quite this involved with the same kind of result. We can look in the textbook for some non-homework related problems. If we want to go over some more. So you just go non-terminal by non-terminal, and you're going to take the largest value. So we would need a table, an LL5 table, where we would have a single row and a number of columns to distinguish every possibility of 5 characters. That's a very long table. So eventually it starts to make more sense to do this variable by variable like this. But if you actually want to go do this, you'll need to store all of these results somehow. What is possible to derive? And then you would have some kind of table that is. You can see that this can only really produce AAABC or AAABA as this C becomes something that starts with an A, or this AAABA. All right, we will come back to this, especially in our review, if we want to get another example. We do have Friday's review session to do this, and if you have questions about getting any of your homework done, we can work through an extra example in office hours maybe. Oh no, I did not animate this correctly, but not too bad to get the grammar first. So next question I have for you. LL of K for what value of K? Any guesses? Guesses for 2 and 3? the hint for this can be found right here. Okay. There is no K, that is correct. These are the two troubling productions.
So, especially because they're like things that you can make one, you make the same shirt from either of those.
Yeah, so basically, let's say we have a look ahead of two characters. We look ahead and we see AA. And what's on top of the stack right now is an A. So we need to now replace this A with something that's going to produce AA. Well, we could apply this first production, which puts us in the same position, so we could apply this production or this production. Right, so on the left-hand side, if you wanted to do this, we would have A, arrow, AA, arrow. Now, we don't know if it's A capital A, or A capital A. We have ambiguity there at two characters.
So it's like four, you have no idea.
Yeah, we add a third one. So, okay, well, now we could be, I guess the other half of this, yeah, we generate this from the left-hand side, or we could generate it from the right-hand side. So we still should have A, arrow, A, and now we're going to say that this could now branch either way into a capital A from here, or a capital A from there. And regardless, we still got those two A's. So you can see that we can generate them in four ways between these two. So now we go to 3, and we can now expand each of these out into 2 possibilities. And every one of these 8 would produce AAA as the beginning. And now there would be 8 possibilities for a branch through this to produce that. And then you add a 4th A, and there would be 16 possibilities, 32, 64. It's never going to be resolved no matter how many A's you look ahead, because you can always, via either of these, produce an A and put yourself in a position where you're ready to produce the next A.
So is it LL of 0 or LL of
It is LL of infinity, or not LLK for any K would be the better. It's not an LL grammar. So stating that, even stating that it's LL of infinity would be contradictory. So the result is that this is not LLK for any K. So you just basically have to show a looping process. And if you really want to get mathematical, this is a proof by induction. But it's enough really to show that here's the starting point. You can get yourself in a loop where you're in the, it's kind of a recursive, the same problem. I need to distinguish now for this A between the next A that we're going to see. And you can see how this is kind of a recursive problem. If we take this problem right here, the problem is within the problem. When you find that, there's going to be no constant number of applications of that recursion that allows you to answer that problem. So if you can find a way to show that or argue that, then you can show that a grammar is not LLK. But it rests in that recursion. Questions on this derivation before I erase it? So I don't need to consider any of the rest of this. I've already shown it within this subproblem. All right. That is the end of my examples for LL. So now I ask people, do we want to start learning about LR parsing, or do we want to go back and get another example of LL parsing? So things to note, LR is not on the homework, it's not on the study guide, it's not going to be on the exam. It's presented because it is the single most complicated thing we've gone over in the class, as well as it pairs very well with LL parsing, and it's actually more frequently used. Even though it's more complicated, more grammars are LR grammars than LL grammars. They're not the same subset. So you can find and look at more grammars in linear time with LR parsing than you can with LL parsing, but it's more complicated as the trade-off. So we can explore that. We can go back and get more examples on LL, and we have today and Wednesday and Thursday to do all of that. So we have time. Is there a preference?
If we want probably more examples.
More examples of LL? Yeah, let's go take a look at the homework and book. So I'm gonna quickly go do that, and we'll come up with a practice problem. While I'm here, I can change the due date. If we have just the oh, there's closure problems. We do need to get to LR parsing, at least the start of LR parsing. I'm not sure there's a problem about LOK for non. There's one that says not L, just show that it's not LL1, but nothing that says it's LLK for what value of K. Yeah, I do think we need to hop into LR, looking at this now. Nothing that does the whole LR process, but there's some of the preliminary work that we need to get to. My apologies, I should know this better off the top of my head. All right, so we'll start with some of the motivation and ideas, but I just gave you some of it. So we saw that there could be a grammar that's not LLK for any K. That means we can't use the LLK algorithm on it at all. It's never going to resolve into a table that we can use for lookups to show that we can go over and find the membership problem in linear time. So we can use an LR grammar and see if we can build an LR table for it rather than an LL table. So let's look at, I guess we started last time looking at the conversion process between the context-free grammar and the NPDA, and we modeled the process that we ended up using. We're going to start there again, but we're going to tackle it from a different direction. So let's come up with a separate algorithm for constructing an NPDA from an associated context-free grammar. And this is going to be one that models LR instead of LL. We're going to use the same three states, Q0, Q1, and Q2. In LL, those three states, we moved from Q0 to Q1 when we pushed the start non-terminal onto the stack. We did a bunch of processing in Q1, and then once the stack was empty, we transitioned over to Q2, and if there were no other symbols left in the string to read, then we could accept. On the other hand, for this we're gonna be do most of our work in Q0 before we even move. As soon as we move to Q1, we're almost done. So what do? We're gonna look at every production in the grammar. So we have non-terminal, arrow, some number of terminals and non-terminals. We're gonna call this x1 up to xn. For every one of these productions, we're going to add a transition in Q0. So from Q0 to Q0, we're going to read nothing from the string. We are going to try to pop all of those symbols, x1 all the way up to xn, and replace it with this non-terminal. Because remember that when we talked about parsing, we said there was a top-down and a bottom-up approach. The top-down started at the start non-terminal and tried to derive the string. And the bottom-up parsing said that we're going to start with the string and try to derive the start non-terminal by kind of reducing the complexity of the string using the concept of these variables or non-terminals as we find ways to make things compressed, reduced. So this is what we're going to be modeling here. So this transition rule is going to say, if we can on the stack, find all of these characters, we could replace them. Of course, can we look at the top n characters of the stack? No. So we're going to have to come up with some way to do that. Some way to know when an entire production is on the stack. That turns out to be a big challenge, but one that we can actually overcome. So this transition type is called a reduction because we're reducing the size of the stack. We're saying we found all of these characters that map to this concept of a variable or a non-terminal. And we're going to replace the right-hand side with the left-hand side in the grammar. So that's a reduction. We can also look over every possible terminal in the grammar and stack symbol. So terminals, union, non-terminals, union, that bottom of stack character that we have. We're going to add a transition rule that we're going to call a shift. So we're still staying in Q0, but if we see the terminal that we're expecting to see in the string, and that stack symbol, top of stack symbol happens to be that same thing, then we can concatenate the terminal and stack symbol and put them back on the stack as we shift past that character in the string. This makes sense though, right? Because we're looking for this one string, this one concatenated string here that we can then replace. So this ends up getting pretty complicated, but just two transitions left. How do we get from Q0 to Q2 and when? We'll transition from Q0 to Q1. We need to see S on the top of the stack. We need to see our start non-terminal. Once we see our start non-terminal, non-deterministically, we can choose to either continue to try to reduce that, or we can go check and remove it. If we remove it and end up with a bottom of stack character, then we can accept. So that's what Q1 to Q2 is going to be doing. So once we remove that S, we're in Q1. We look at the bottom of stack character, or we look for the bottom of stack character. If we see it, we transition into Q2 and can accept. If we don't, we just reject from there. That says some other thread that's working on reducing that start non-terminal further down into another start non-terminal if we accept. If we can't accept. How are we doing with the concept? So we're going to be modeling bottom-up parsing now by trying to do this concept of a reduction and a shift. We're going to be concatenating and producing strings and then looking for those strings that map those productions so that we can remove all of those characters from the stack and start to move past some characters in the string. But we're going to be doing it multiple characters at a time as we are able to produce the right-hand sides of productions that we can reduce into the left-hand sides of those productions. Thumbs, numbers, how we feeling about the concept here? This one's challenging.
An example, polygon.
Yeah, that is exactly what we're going into next, but the goal is that we are trying to reduce this. So all right, let's try to create an NPDA that models this process. So we start with those three states, Q0, Q1, and Q2. We're going to add a bunch of transition rules to Q0. So the reduction transition rules are going to be all of those that allow us to replace a right-hand side with a left-hand side. So first of all, how many of them are there going to be? How many different ways are there to replace a right-hand side with a left-hand side? Four of them. You can replace this right-hand side with this left-hand side, this right-hand side with the left-hand side, right-hand side with the left-hand side, right-hand side with the left-hand side. So there are going to be 4 rules. So again, we're always going from Q0 to Q0, so there are loops. And in none of them are we making any shifts in the string. These are all reduction-based rules. So because of that, the second position here is always going to be lambda. This just tells us we're not moving past any characters in the string. But we're going to take each right-hand side and replace it with the associated left-hand side. So Q0, lambda, right-hand side, Q0, left-hand side. That will always be the case for any reduction rule that you write. Then we need the shifts. And this tells us how we move past characters in the string. So basically, we can imagine there being any string that starts with an X. Or it starts with an A and is followed by anything. The idea is if there's this string that appears somewhere, we can remove that A from the string, and we're going to move past the A and push X onto the string, everything that followed the A in terms of that string. We can do the same thing for any place a B appears, any place a C appears. And usually this is how this is written instead of there being a bunch of different transitions, but do note that in a hard-coded system that there are a bunch of transitions for every possible X that could reasonably appear in the system. But it's okay to write it like this. You know what you mean. X can be any terminal, non-terminal, or the bottom of stack symbol possibility. Then we have the final transition rules that get us to Q1 and to Q2. Remember that when we see an S, the question is if we get rid of that S, is the stack empty? If it is, then we accept. If not, then there's some more work to reduce this down into another start non-terminal. Like we have a rule S arrow A capital SB. Let's say we read past an A and here's this S. The question is now, if we resolve this, are we done? If we get rid of that, are we done? But no, we have something left that follows it. The stack would not be empty. We could not accept the string that ended here. We would have to make this right-hand side, condense that into this S, and then see if it could go away. So we end up with an NPDA that looks something like this. Note the use of predicate logic to say for all X in T union B union the set that is the bottom of stack symbol, all terminals and non-terminals, and bottom of stack symbol. So rather than draw out a bunch of possible transitions here, you just leave it in predicate logic form.
For just two different one group, and then just like list all of those of the user. I just like did like a big error back or something.
You would have to,
Or does it have to be a separate arrow for every single?
I'm trying to think what the logic would be like. So you'd have to find some way of saying some logical statement that says for every possible terminal concatenated by some X. So yes, logically, you could do this with a single arrow. You would just have to make sure that, don't have a paragraph that explains it, make sure that you're using some kind of logical statement.
Well, no, if I take like a single arrow and have like AX, and then underneath it BX, and underneath CX, so I just like list them. It's like this one arrow, this one represents all of these, could you write that instead of that right also?
You could comma separate them such that you'd say, we are basically out of time, but if we were to write that, you would say something like S such that all right, you could even go TX such that T is in the set of terminals. And then X would be defined here. You did that would be a logical representation of this is such that we have some terminal followed by that. And this is all possibilities of that. Suddenly, if we didn't have this as a possibility, you wouldn't be able to say that because this is not, you'd have to find some other alternate logical way to state that. But you could do that. Make sure it's correct. I find a lot of times people try to, I'm not sick. People try to reduce the amount of work, but end up making it wrong by trying to make it less complicated, and it ends up being more complicated to figure out how to word it rather than just draw 3 arrows. But if you're able to do it and it is correct, by all means. All right, we'll pick this back up tomorrow and get into some more LR details, learning about closure. See you tomorrow for that. I'll be in my office if anyone has questions.